Get this started. So in the electromagnetic spectrum, you have waves that radiate from a source, and the waves are all different types of energy. So that's one variable, is how much energy, low or high. And so you guys should understand, and I hope you do, that these are the lower energy waves over here on the right on this spectrum at the top. Radio waves, microwaves, infrared. You don't need to protect yourself from any of those because they're lower energy. And this includes visible light. So radio, microwave, infrared, and visible light, they're lower energy. And that's not high enough energy to break bonds in molecules. So go tell your roommate, go tell your parents. I actually just reminded my mom of this a week ago. It's okay to stand in front of a microwave. If you are not standing in front of a microwave, then you might as well not stand outside in the sun, which has UV energy. So the higher energy, UV, X-rays, and gamma, this is the symbol gamma in the Greek alphabet, that's higher energy, enough energy to break bonds in molecules. Now, you guys have some exposure to UV on a daily basis when you're out in the sun, and that's okay. There's beneficial effects to UV breaking bonds in molecules and initiating reactions like the vitamin D reaction. So then there's X-rays. You can be exposed to some X-rays as well. You can be exposed to a certain number of X-rays per year, and this is why the dentist and the doctor keeps track of how many X-rays you're exposed to per year. So it's not that this is going to kill you. It's not even fatal. It's just that over time, there's an accumulation of bonds that are broken in molecules, and we'll get to how that leads to skin cancer and get to there. So these are lower energy on the right and higher energy on the left. And we'll look at different electromagnetic spectrum views where sometimes it's flipped. So one variable is these are all types of waves, and they have lower energy or higher energy. Two other variables that I just mentioned are the wavelength and the frequency. And so the relationship between wavelength and frequency is inversely proportional. If one is low, the other's high. If one is high, the other's low. And so this is showing on here. I want to find this. Okay, so here is showing a wave of the wavelength 570, no, 630. So what's happening is that I am adjusting using the slider bar. So these are colors. Okay, so now I'm on this middle bar. These are colors in the visible light spectrum. So here you have the backwards version. Here's Roy G. Biv. So red, orange, yellow, green, blue, indigo, and violet. And so what these are they are amounts of energy. This is the purple is actually the low, violet is actually the highest energy. It's over there on the UV side. Those are the higher energy. And then red is actually the lowest energy color. And so this all fits in right here, this rainbow of colors. When you combine all of them, it's white light, visible light that we can see. All these other ones we can't see. We can't see the lower energy. We can't see the higher energy. So the higher energy over here, this is the highest energy color. And you can see that it has a certain wavelength, which is this distance between these successive peaks. And this wave continues indefinitely in both directions. And so for the wavelength, this, as you go to the lower energy, what is different for the red? Well, we know it's lower energy. It's on this side. It's closer to these guys, which are lower energy, the radio waves, microwaves, and infrared. Lower energy, what happened to the wavelength? Well, the distance between those peaks from these two stretched out. So this is a bigger wavelength. And so what happens with the wavelength relationship to frequency is the more of these waves that are more spread apart, you have a higher or longer wavelength for this red colored wave. And as a result, you have less of these waves passing through one point, choose the point down here, less of these waves pass through one point in 1 second. So wavelength high means frequency is low. Let's go back over here to the higher energy purple. So that is a lower wavelength or shorter wavelength comparatively. And so shorter wavelength, these are closer together. Well, you pick one point, a lot more of these waves pass through in one point. And so this is A lower wavelength, a short wavelength, means a high frequency. So they're inversely proportional. And I also wanted to show you this so you understand that these energy amounts, so these are higher energy, and then this continues on to lower energy. So the colors of light are related to amounts of energy as well. Okay. So this is the first of today's lecture worksheets. This is 3.1 lecture worksheets today. And I had started with the simulation. I actually do have a couple more of those simulations to show you to really understand the relationships between energy, wavelength, and frequency. It's both qualitative, like I was showing you with the waves, inversely proportional, directly proportional, but it links back to these equations. So why is wavelength and frequency inversely proportional? It's because of this equation. Or why is energy and frequency directly proportional? It's because of this other equation. So these are two equations that you'll get some practice with, not just in lecture, but also in an upcoming lab. So we know that electromagnetic radiation. So don't be scared by the word radiation. These are in the electromagnetic spectrum, and you'll notice that I use EM to refer to electromagnetic quite a bit because it is a big, long word. So the EM spectrum, this doesn't want me to fit in the letter C. Okay. I'm putting it down there. The EM spectrum is the electromagnetic spectrum. Radiation are these waves of energy. And so these waves are characterized by the wavelength. And get used to this symbol for wavelength. I'm going to write it right above it. It's that upside down Y. It is the Greek letter alphabet lambda. Okay, but it's an upside down Y. And the wavelength is going to be in units of meters, or some unit with an M in there. So it might have a metric prefix in front of it, like nanometers. Okay, so a wavelength could be expressed in nanometers, or any metric prefix with that, like centimeters or picometers. So that's wavelength expressed in some form of meters. Frequency. So frequency is that other Greek symbol. This is that cursive V highlighted in blue. It's called nu in the Greek alphabet. And the frequency has units that are 1/s, which stands for 1/seconds, or hertz, Hz. So the relationship is that 1 Hz is equal to 1/s. And this is also written sometimes as s to the -1. And so this is frequency is how many waves pass through a point in 1 second. And then you have a couple of constants, and this is one of them. The speed of light is c. Now, I don't know why it got the letter c. It should have gotten an s, but it got a c. It is a c. And that speed of light is a number value that you will always have, 3 × 10⁸. And notice the units are meters over seconds. Okay. Those units will become important in canceling units when working with these equations. So here's this relationship. This is an equation that you don't need to memorize, but you do need to know how to use it. Now, what is there to understand how to use it? Well, basically looking at it and seeing that these are variables that represent wavelength and speed of light and frequency. So what this says in words is that the speed of light, that value 3 × 10⁸ meters per second, okay, is equal to wavelength times frequency. And so the wavelength is that symbol, the upside down Y, the lambda, and then frequency is that nu, the V. So that speed of light you will always have. And what you can do is use the speed of light and solve for either wavelength or frequency when you're given the other. And this reason why wavelength and frequency are inversely proportional, why is one high and the other's low, is because of this equation. When you're multiplying these two variables and they're always equal to the same one number, well, that kind of constrains you. If one is high, the other one has to be low if they're always going to be equal to the same number when they're multiplied. Or if one is low, the other one has to be high in order to always be equal to the same number. What this also means is that when you have all these different waves, whether it's a radio wave or an X-ray or a microwave, that all these waves travel at the same speed, the speed of light. So even though it's called the speed of light, it's actually the speed of all waves in the electromagnetic spectrum. Okay, and so they all have to fit within this constraint. They all travel at the same speed, and we can't see them. You can only see the visible light, but they travel at the same speed. But what's different about them is they have different wavelengths and frequencies. Okay, so get used to that value for C. The other equation we have is a relationship between energy and frequency. So this is energy is E, is equal to this constant. So this is called Planck's constant. I'm just going to write the word constant, and this is times frequency. So get used to that symbol, that V for frequency. So you need to get used to the symbols, and you also need to get used to the units for these. So energy is in the represented by the uppercase E, is in the units of joules, J. That's uppercase J. And then you have that constant, which is actually a really small number value. It's 6.63 times 10 to the minus 34 J times S. So this relationship, this equation basically is that frequency and energy are directly proportional. When you take frequency, it's basically equal to energy when you multiply it by this super small number. So if one is high, then the other is high. The other one is low, the other's low. So we will work with the equations now, and in the same process that I had previously back in module 1, where when you're given a word equation, you want to identify the parts. This first thing that reads, calculate the frequency, that's actually the unknown. When it says calculate the frequency, that means that's your unknown, is frequency. Now, more useful than the word frequency is the symbol for frequency. So you want to write the symbol for frequency instead of the word, and the symbol for frequency is that cursive V. Why is the symbol more useful? Because it's the symbols that are represented in the equations. And so when you're looking for an equation to use, you're not going to be looking for words. You're going to be looking for the symbol for frequency. Okay. The next part in this word equation is that they're telling you the wavelength is 5m. So that's known information. So they're telling you the wavelength. And instead of the word wavelength, you want to write equals. So that's an equal sign. And then the variable, that is the Greek letter lambda, that upside down Y, because it's the symbol, it's the variable for wavelength that's going to be more important to look for. And then you want to write what that's equal to. The wavelength is equal to 5 and the units of m. And so remember m, this is the units for meters. And that also should tip you off. Meters are what length is measured in. So the wavelength is measured in meters, and this one does not have any metric prefix with it. Okay, so if you're going to solve for your unknown, you're going to need an equation. You're going to need an equation with both frequency and wavelength. Of your two options, this is the only one that has both frequency and wavelength. This other equation, the lower one, has only frequency. It does not have wavelength. So you need both. So the equation you're going to use is this one. So just copy it. C equals wavelength. So that's that lambda upside down Y times frequency. Okay. And so the first thing I want to do after I have this equation is I want to see if the thing I'm trying to solve for is isolated. Isolate the unknown. The thing I'm trying to solve for is this frequency. Here it is right here. It is not isolated. It is not by itself on one side, the equal sign. So I'm going to first isolate the unknown. The thing I'm trying to solve for, the unknown, is this symbol for frequency. So isolating it means that I need to rearrange this equation. So let's do this over here in green. This is C equals lambda over frequency. I need this to be by itself on one side of the equal sign. So I need to get rid of, on this side, the lambda. So get rid of the wavelength by dividing both sides of the equal sign by that. So then this allows this to cancel out. And so what you're left with is this is by itself on one side of the equal sign. On the other side of the equal sign, you have C over wavelength, C over lambda. So that's good. Once that's isolated, now you can solve for it. So if this is C over lambda, you want to put in the value for C. So the value for C is the speed of light. And so remember, even though it's a variable, that C at the top, even though it's a variable, it's not, it's actually a constant. So that's what you got to get used to is that C value is a constant. It's 3.0 or just 3 times 10 to the 8th and meters over seconds. Okay. And then on the bottom is the amount of wavelength. The value for wavelength is 5 and then M. Okay. Now I'm not going to go to the calculator yet. First, I'm going to look at the units. So just looking at the units is that this is a fraction, meters over S, inside of a fraction. It's in the numerator part. It's in the top part. So what happens to a fraction inside of a fraction is that the denominator moves. So this S, circling this in purple, moves down and it becomes one fraction. So get rid of that. So what you have is meters on the top and then meters times seconds on the bottom. Okay, so I dealt with the units first, and basically by compressing a fraction within a fraction to make it just one fraction instead of a fraction inside of a fraction. So this is no longer up here and it's down there. And this allows me to cancel meters. And what that means of the units is that, put an equal sign, what you have is nothing on the top because this is crossed out and that's crossed out. And on the bottom, you don't have an M anymore, you just have an S. So that is 1. You can always put in a 1 or take away a 1, but now I'm putting in a 1. And that 1 over S is good. Those are the units for frequency, because remember, the units for frequency are these possibilities. 1 over S is one of them. Okay, so Hertz, 1 over S, or S to the minus 1. So once the units check out for the thing you're trying to solve for, 1 over S of the units for frequency, then you can go to the calculator. So the calculator is 3.0 divided by 5. Oh, actually, let me put this in the calculator. So this is 3.0 divided by 5, or 3 divided by 5. And that is 0.6. 0.6. And this is still times that 10 to the 8th. Don't forget that. And that's 1 over S. So this is a number that is calculated, and every number that's calculated, you need to check your sig figs. So when this is multiply or divide, it's sig figs, which is the majority. And this original number value, which is 5 meters, has 1 sig fig. So your answer needs 1 sig fig. Okay, and that's fine, leaving it at 0.6. because the leading 0, the 0 on the left, is not significant. So just that 0.6. Now, if you wanted to convert this to scientific notation, this would be 6. And this would be, this coefficient gets smaller from 0.6, or sorry, the coefficient got bigger from 0.6 up to 6. So the exponent needs to get smaller down to 10 to the 7. And the units are still 1 over S. Okay, so that would be your answer in scientific notation and with 1 significant figure. Okay, so are you guys ready to look at the second one? This is...
I have a quick question.
Yes.
Because you went from 0.6 to 6. How come we didn't just make it 1, round up to 1?
Because this is already 1 significant figure with the 6. And so that leading 0 is not significant. So you don't have to do anything if you already have just the 1 sig fig.
Oh, okay. Okay, that makes sense.
Okay.
Thank you.
Okay. So thank you. Let's make sure I don't have anything in the chat. Okay. So let's take a look at the next one. So this is another example word equation. It has a microwave, emits waves of 5 times 10 to the minus 2 meter. So when you have a number value with units, that's known information. Okay, so unlike the first example, the first thing that popped off was a question. Well, the first thing that pops out here is this number value, 5 times 10 to the minus 2 meters. Well, that's fine. It's a number value, but what does it represent? If you're given a number value with units, you want to write what it's equal to. And you need a symbol. It's got to be one of those in these equations because we're going to use these equations. So which one is it? Well, how do you know if it's energy, frequency, or wavelength? You can be guided by the units. So that unit is an M, and M is meters. Okay, meters are the units for wavelength. So this must be wavelength. And you're guided by the units, M. Okay, and so you don't want to write the word wavelength. What you want is the symbol for wavelength, that upside down Y, the lambda. Okay, so that part is not written in the word equation, but you need to start understanding that units will let you know what the information is, what the variable is. Okay, so then the question says, what is the energy? So that's where the unknown comes in. They're asking you what the energy is. Instead of the word energy, you want the symbol for energy, which is an uppercase E. Okay. So how are we going to solve for energy? Well, there's one equation. There's only one equation that has energy in it. It's the second one. So there's two equations, 1 and 2. Only the second equation has energy in it. So you're going to use this equation. I'm going to write that one down. E equals H times frequency. And I'm going to use this equation to solve for energy. Okay. But I first need to use the other equation, C equals wavelength times frequency, to solve for frequency, that symbol for V. Why do I need to do that? It's because the thing I'm trying to solve for, energy, circling it in red, is in this equation. So I could use that equation. If I had both the value for H, which I do have, H is Planck's constant, that's 6.63 times 10 to the negative 34 J times S. So I do have H, but I don't have that symbol. I don't have frequency. Okay, what I have is wavelength. So that therefore I can use the wavelength. I can use the value for C, the speed of light, reminding you it's 3.0 times 10 to the 8th meters over seconds. That's C. I can use both of those, the wavelength value here and the value for C, to solve for that frequency first. Okay, so let's do that first, which is using the version of the equation where I had already isolated for the frequency. So that was C over, so I used this one. Okay, so this is C over wavelength. So this is the value for C, 3.0 times 10 to the 8th meters over seconds on the top. And then on the bottom is that wavelength that's 5 times 10 to the minus 2 meters. Okay, so the same thing, I'm going to look at the units first. So this meters over S is a fraction inside of a fraction. So what that means is the denominator moves. This S on the bottom moves down, becomes times S, and you can cross it off up there. And so meters and meters will cancel out. The units are going to be 1 over S. Okay, so then you've got the number values to divide are 3 divided by 5, and that's still going to be 0.6. This time you have 10 to the 8th over 10 to the minus 2. And so looking at the exponents, this is 8 minus minus 2. So the two negatives make it a positive. And so 8 plus 2 is 10. So this is 0.6 times 10 to the 10, 1 over S. And that, remember, is equal to the frequency. We're not done yet because we are still trying to solve for energy. So then we're going to use that frequency to solve for the energy. So this is the value for H is 6.63 times 10 to the negative 34 J times S. And then use that number value that you had just solved for. So that's not the answer because this is only the halfway to get there. So 0.6 times 10 to the 10, 1 over S. Okay. So before going to a calculator, look at the units. You've got J times S and then 1 over S. So this S cancels out with that S. You have one that's a numerator and one that's a denominator. And so what that leaves is the units J, and that's good because units J are the units for energy, joules. Energy is in units of joules, or J. Okay, so once the units check out, then and only then do I go to the numbers. So the numbers are the 6.63 times 0.6. So 6.63 times 0.6, and that's 3.978. Then you've got the 10 to the negative 34, looking at it over here, multiplied by 10 to the 10. Now this time you're not dividing powers of 10, you're multiplying powers of 10. And when you're multiplying, you add the exponents, writing it down over here on the right. So adding the exponents, that's negative 34 plus 10, or negative 24. So this is going to be 10 to the negative 24 power. Okay, so this is negative 24. And the last thing we have is, let's make sure this is going to be sig figs. So our original number value is 5 times 10 to the minus 2, way back up there where the known information is listed. So that 5 has 1 sig fig. So our answer needs 1 sig fig. So this is the 3 would be the 1 sig fig, but you can see the digit right after is a 9. So you get to round up to 4 for the 1 sig fig. And this is still times 10 to the negative 24 and joules. Okay, and so that is with one significant figure, and it's in scientific notation as it's written, 4 times 10 to the negative 24 joules. Just looked at. So wavelength and frequency, they're inversely proportional, and energy and frequency are directly proportional. And so we're going to summarize all of this on this worksheet. So we're talking about the electromagnetic spectrum. And remember, I use EM to shorten that big long word, electromagnetic. But those are all those types of energies. Those are types of waves that have different energies. They also have different wavelengths, and they also have different frequencies. And they're called radiation. And remember, don't be afraid of the word radiation. It just means it's coming from a point. It's coming from a central point. And radiation that is dangerous, that nuclear radiation, we'll get to. So this electromagnetic spectrum on the right here, when you are given a spectrum, you want to orient it. Does it go from low energy to high energy, or high energy to low energy? And the way to orient yourself is to find the low energy radio waves. Those are always going to be at one end. So radio waves at this end means that on the left side are your low energy. And going to the right, always on the other side, are these guys. These are called gamma. That's that symbol gamma. The gamma rays, those are high energy. They're always going to be on one side. Okay, so you're always going to have radio waves on one side and gamma rays on the other side. So you just have to decide which side is low and which side is high, because you could flip this and list it from high to low or from low to high. And this one is listed from low to high. Okay, and so you can see everything in between on there. There's the microwaves. IR is infrared. And then you have visible light. That's usually approximately in the middle, right? And then you have UV, that's ultraviolet. And then that continues on to X-rays and gamma rays. Okay, and so the relationship between energy and frequency, these are directly proportional because of this equation that basically says when you take frequency and you multiply it by this constant, it's going to be equal to energy. Okay, so if you have a high energy value, it means that there will also be a high frequency. Okay, and this low energy means it's going to be a low frequency. Okay, so looking at a wave that has high frequency would be a wave that there are a lot pass through in 1 second. That would be a high frequency wave. Compared to a low frequency wave, that would be less waves passing through in 1 second. Okay, now in this next equation, this was where wavelength and frequency multiplied together are equal to the speed of light. And so that, because they're multiplied together, always have to be equal to the same one number, that value for the speed of light, means that that makes them inversely proportional. So a high wavelength or a high wavelength or a long wavelength, that's another way to say this, is going to give you a low or a short frequency. Okay, or a low wavelength, which is also a short wavelength. This would give you a high or long frequency. Okay, and so that's the same thing. A low frequency would be these waves, and a long frequency would be these waves. Okay, so this is, sorry. So the high wavelength versus the high frequency. Okay, so the relationship between energy and wavelength is not in one of those equations. It is something that can be inferred from those equations through energy, because energy and frequency are directly proportional. They're basically saying they're equal. That means you could just replace energy in and say that energy, or E, is also inversely proportional to wavelength. Okay, basically you can replace in energy for frequency. Okay, so these guys, these higher energy waves versus lower energy waves, back up here, this low energy means that you have a low frequency, using the symbol for frequency, and a high wavelength. And so that's why this says a longer wavelength on the left side. Versus over here, high energy means a high frequency, and high frequency means a low wavelength. And so this is also indicated here. There's a high frequency on that side, the high energy waves. Okay, so there's different ways to look at an electromagnetic spectrum. But first you want to orient yourself. So here's another electromagnetic spectrum. In this one, the visible light is broken out. Okay, so the visible light is approximately in the middle, usually off to one side. But you first want to decide which is the high energy side, which is the low energy side. Okay, so gamma rays, these are on the high energy side. And then this is listed from high energy to the radio waves on the low energy side. So this is going from high down to low, as opposed to the other one that was from low up to high. This also includes the visible light broken out. So I'm going to add that down here. The higher energy is on this side, and then the lower energy is on this side. It's just broken out increasing that on this already high to low spectrum. So this, remember, red is the low energy color, and violet is the high energy color. Okay, and so just outside, just higher than violet is UV. So that's UV energy is higher energy than visible light. So circling that in red, those are the UV rays that are just higher energy. So everything that's UV and higher, so UV, X-rays, gamma rays, those are high enough energy to break bonds in molecules. Everything that is visible light and lower, those don't do anything to you. So just outside of the visible light range, this was here, is, okay, red is the lowest energy color, and just below red is infrared, or IR. So that's kind of useful. So let me point that out on here, is that you have the visible lights broken out here. Just above it, just higher energy is UV, and just lower energy is this one, infrared, IR. But that's what sunlight has. Sunlight gives us all three within that little narrow range. Sunlight has UV, visible light, and infrared, or IR. It gives us this little range right in there. Okay, and so The majority of sunlight is infrared and visible light, and just a small part of sunlight has UV. It was broken out. It's about 8% is UV. And it's not even the dangerous part of UV, because remember, the atmosphere protects us from the high energy UV, which we'll get to. But in this, we can answer some questions now that we are looking at this spectrum and we understand how it's oriented. This is the visible light. It has the Roy G. Biv broken out. And you can see the wavelengths are in nanometers. So remember, length in nanometers, or nm. Okay, and so those are 400 to 700 nanometers about is your wavelengths of visible light. Okay, so now let's answer some questions. So based on this, image, we can answer these questions. Which has higher energy? Now that we've oriented, right, low energy versus high energy, which has higher energy, the radio waves or the microwaves? Well, the higher energy here, you've got radio waves, and oh, I should put microwaves is right about in here usually. So yes, microwaves are higher energy than radio waves, okay? But if you're in number 2, which has higher energy, the microwaves or sunlight? Well, remember, sunlight is here. And so sunlight has higher energy than microwaves, okay? Which has higher energy, the blue light or the green light? So when you're looking at this, where you had already written out higher energy to lower energy, so here's the blue and here's the green. So you can see that the blue light is higher energy. Which color of light has the longest wavelength? So we can do this by looking at the number values, or you can do this by understanding the relationships. So a long wavelength means that you are looking for a long or a high wavelength is a low frequency because they're inversely proportional. So a long or high wavelength, a low frequency, and you're looking for a low energy. And so the lowest energy color is red. And you can also see that has the highest or longest or greatest wavelength value of about 700. Now that's kind of interesting. It's always been kind of interesting to me that red light is the highest energy color, because red in psychology or the neuroscience, red is an activating color. It's a hot color. It is something that's used on stop signs and stop lights for a reason, because the brain sees red and it responds. But it's not having to do with the physics or the chemistry or the calculations. By its number value for energy, red is the lowest energy color. So it doesn't have anything to do with the energy. It just has to do with that's the way your brain works when it sees the color red. So this is number, and so that's also, if you have ever heard of, in photography, you have a room that you can go into that's lit by a red light. So photography has film that is basically when you take a picture, you're exposing it to energy, and that causes the picture to take on the film. Well, if you use a red light, that's low enough energy to not expose your film in developing film photography. Okay, so the highest energy color is violet, and just outside of it is higher energy UV. Okay, and then this question: which has the longer wavelength, blue light or infrared energy? So again, when you're talking about longer wavelength, this is longer wavelength, which means high wavelength. And the relationship going back to energy, high wavelength means low frequency. Low frequency means low energy. So which one they're asking about here is which has the lower energy, basically, blue light or infrared. Okay, and so you can see that lower energy, you've got infrared here, circling this in green, and blue light is inside of here in this broken out. So blue light's here. So lower energy is going to be that infrared. Okay, that's just lower than, is just lower than visible light. And that's where blue light is part of. Okay, so basically what I'm saying is when they're asking you long wavelengths, short frequency, high frequency, you want to relate it back to energy from these relationships. Energy and frequency directly proportional, frequency and wavelength inversely proportional. Okay, so visible light all around, you can't see it, but it doesn't do anything to you. Doesn't do anything to the molecule, but as these guys, so going down to radio waves, that's the lowest energy. So this lowest energy, when radio waves, you're being hit by radio waves right now, nothing's happening to you, nothing's happening to the molecule. That means nothing's happening to you. It's not dangerous. Radio waves are low energy and don't break bonds in molecules. What do microwaves do? So a microwave doesn't break bonds in molecules either. A microwave causes this particular molecule to rotate. So molecules that are specifically polar molecules, we'll get to that definition, will rotate in a microwave. Not all molecules will rotate in a microwave, okay? But that's all it does. It doesn't break any bonds. Let's move on up to infrared. Infrared is heat energy. So heat energy we get from the sun, and that's important. What did the infrared, that was a wave, let me get this come out again. So infrared is a wave and it's going around, and what does it do to you? Well, here's what it does to this molecule, is it causes the molecule to vibrate. The bonds are vibrating, but they're not breaking, okay? And this will become important in understanding how carbon dioxide and other gases are warming the atmosphere. So this is vibration. That's what infrared, what heat does. This is heat from the sun. Infrared from sunlight causes molecules to vibrate, the bonds to vibrate, okay? What does visible light do? Nothing, just passes through, doesn't cause rotation or vibration. But let's take a look at what does UVA energy do. Okay, so this is UVA now, and still doesn't do much to that molecule. So UVA is the lowest energy UV, and it is basically not that dangerous, okay? Over time, UVA exposure does cause skin aging and wrinkles, and over time, skin cancer. Higher energy, moving up, we have UVB. And what does that do? Oh, cause that bond to break. So when bonds break, now you're talking about the types of bonds that break are in DNA that can lead to skin cancer long-term, not right away, but long-term exposure. Enough bonds broken in one's DNA in your skin can lead to skin cancer. So that's what UVB does. Let's reset this. UVC, so that's the highest energy UV, and we're protected from that. Thank God, because UVC breaks bonds immediately, okay? So UVB, I wanna go back to, UVB can break bonds in molecules, and it did that right away, but it's not gonna break both of them, versus if I let this sit around long enough, UVC will break all the bonds in this molecule, okay? So fortunately, we're protected from UVC. Earth's atmosphere absorbs it. We're protected from X-rays and gamma rays basically by not being exposed to X-rays or gamma rays. Okay, forgot to record all that. We don't have any UVC hitting us because of the ozone layer. And so we've got, this is this simulation. I've got UV in the atmosphere, and I want to, I think, show here. Okay, so this is a thing that emits radiation. The sun is an example, and this sun emits from sunlight UV, infrared, and visible light. Okay, so let me see what happens when I show this. So zooming in, what we have coming from the sun, we have UV energy, we've got visible light and infrared. The majority of what we have in sunlight is infrared and visible light. Those are low energy and they don't cause damage. That UV, the 8% of what we have coming from sunlight, that little fraction of it is coming to us. And fortunately, the highest energy UV, UVC, is completely absorbed by the stratosphere. Okay, so that's all natural. And we have no UVC basically coming to us, but we do have some UVA and UVB. So that's, here's this electromagnetic spectrum. But what we have going, no, this one. So we have some UVA and UVB. So I talked about that. When you go look at your sunscreen, does it say UVA and UVB protection? Does it say broad spectrum? It better, because if you bought it, that's what you need to protect yourself from. You don't need to protect yourself from UVC or from visible light or from infrared or microwaves. What you're protecting yourself from is UVA and UVB that hits us and comes with sunlight. Okay, so this is next one. So I must be wanting to look at this. Okay, so here's this light. What do I want to do? Oh, yes. Okay. All right. So what happens is that UV comes to us from the sun, and ozone absorbs that high energy UVC, and oxygen also does some of the work. And this ozone layer, okay, show that ozone layer. Okay, so that ozone layer absorbs all of the UVC. So no UVC comes down into Earth. The ozone layer absorbs most of the UVB. So what exactly is going on in the ozone layer? It's not sponges. It is the molecules of oxygen and ozone in this layer. So mostly ozone, that's O3, is absorbing UVC and most UVB. So UVA is not on here because UVA completely passes through. And so that's what we get down here in the troposphere. We get UVA and UVB down here, but we don't get any UVC. Okay, so let me show you this. Okay, so what happens in your skin is that UVA and UVB is what reaches us down on Earth, and UVA penetrates further down. UVA causes the longer term damage like wrinkles and sunspots, versus UVB just hits the surface. And so that causes the suntan, sunburn, and vitamin D production is right there happening at the surface. Okay. And so this is what we get down on Earth. UVA passes through the ozone layer. UVB is mostly absorbed and we get a little bit of UVB, and UVC is completely absorbed in the ozone layer, and we don't have any of that reaching Earth. Okay, so here's what you have in the sun. What's going on with the sunscreen is that you put on your skin. And so sunscreen versus sunblock. Can I get this to work? Okay, there are these nanoparticles that are basically, that's what's in sunscreen and sunblock, compounds that are either absorbing or blocking. So you've got these being absorbed, and I don't think I see any of these. This is only sunscreens. Sunscreens basically come in and the UV comes in, and it basically goes and changes temporarily the sunscreen molecule. Okay,